Welcome to Speaker Night at the David Dunlap Observatory online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton, and I am the RASC Toronto Centre DDO Committee Chair and an operator of the 74-inch telescope at the David Dunlap Observatory. Together with our outreach coordinator, Quentin Wayrich, I am delighted to be your host for tonight's lecture. I'm also very excited to welcome you, our viewers, to tonight's talk. If you haven't already, please take a moment to say hi in the YouTube chat and tell us where you're joining us from. This helps us make sure that our technology is working properly. The Royal Astronomical Society of Canada's mission is to enhance understanding of and curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the David Dunlap Observatory, or DDO. The observatory is home to Canada's largest optical telescope. While we miss welcoming guests to the DDO facility, we are hoping to return there soon, and in the meantime, we are happy to bring you virtual programming. We would like to start by acknowledging that the David Dunlap Observatory in Richmond Hill stands on the traditional territories of the Wendat, the Haudenosaunee, and the Anishinaabe peoples, whose presence here continues to this day. We would also like to acknowledge this land is at the meeting place of two treaties, the lands of the Mississaugas of the Credit and those of the First Nations of the Williams Treaty. We thank them and other Indigenous peoples for sharing this land with us. It's my great pleasure to introduce our speaker for tonight's lecture, Dr. Michael Reid. Dr. Reid is an associate professor, teaching stream, in the Department of Astronomy and Astrophysics at the University of Toronto. In his teaching, he specializes in developing astronomy courses that are accessible to all students, not just those in the physical sciences. In his role as the public outreach coordinator for the Dunlap Institute, he breaks down complex ideas such as the Big Bang, black holes, and the search for extraterrestrial life to make them easily understandable by peoples of all ages and backgrounds. Tonight, Dr. Reid's lecture, The Search for Another Earth, addresses the ever-popular question, are we alone in the universe? If you have questions for our speaker, please post them in the YouTube chat. We have two moderators tonight, Elizabeth Reid and Quentin Wayrich will be monitoring that chat, and Michael will have time to take questions from the audience at the end of his talk. Please join me now in welcoming Dr. Michael Reid.
Okay. Hello, everybody. Thank you so much for coming to tonight's event. I'm very happy to be with you. Tonight, I'm going to tell you a little bit about what is the hottest topic in astronomy these days, consumes a lot of the attention of astronomers, which is the search for not only planets beyond our solar system, but planets that might be like Earth. So the motive for this, for astronomers is probably the same as it is for many of you in terms of why you were interested to come to tonight's event. And that is, astronomers are curious to know whether Earth and the life that Earth hosts is unique in the universe. And so we devote a lot of our effort to trying to identify planets elsewhere in the universe and characterize them to figure out whether or not they might be like our own home. So that's what we're going to talk about tonight. Okay, so most of you, probably all of you listening to this, have spent your entire life here, right? This is our lovely home planet Earth. This is a photo of Earth taken by human beings as they left Earth on the way to the moon. And, you probably take this kind of photo for granted nowadays, right? You see lots of representations of Earth like this. But I want you to sort of focus on what's around the Earth in this photo, which is nothing, right? The as we often call it, the vacuum of space or the void, right? What's impressive to me as an astronomer about this photo is that it shows how kind of fragile the life on Earth is. Everything on our planet that is alive and that is sustaining life on our planet is a thin, thin, thin little skin on the surface of the planet, right? You can't even, if you look at the edge of the planet here, you can't see the extent of our atmosphere in the image, but it's that atmosphere that's keeping us alive right now, right? All of the oceans and the forests and everything are, you know, a tiny thin little skin on this rock hanging in this perilous void that would be very, very bad for us if we were to have to encounter it without all of this supporting planetary infrastructure. So our Earth seems to be kind of precious and special and a little bit fragile. But because I'm an astronomer, I'm not going to spend a lot of time looking at Earth. My job is to get you to look the other direction. So if we turn our telescopes out into the universe, what do we see? So this is a very famous image some of you may have encountered before called the Hubble Extreme Deep Field. And it may at first look like a fairly generic image of the sky, but if I give you a sense of how it was taken, it gives you a sense of its importance and what it tells us about the universe. So this image was taken using the Hubble Space Telescope, which is one of the most powerful space telescopes we have, most powerful telescopes, period. And the way it was taken was by pointing the Hubble telescope at a patch of sky that was essentially empty, until that time not really known to contain many objects. So they certainly weren't pointing it at some part of the sky they thought, oh, this is going to be full of stuff. And the patch of sky that it points to is very, very small. So if you were to hold your pinky finger out at arm's length, the patch of sky that this photo corresponds to is about the size of your pinky fingernail. And what they did was open the shutter on the Hubble Space Telescope and essentially leave it open for, weeks at a time, gathering light for a very, very long period of time compared to a typical astronomical photograph. And in so doing, out come all of these details. Now, when you look at the image, you might think, okay, I'm looking at a bunch of stars. And in a sense, you are, but maybe not in the way you're expecting. So all the little dots in this image, the little flecks of color, almost none of those are individual stars. The vast majority of the objects you see in this image are galaxies. So each one of them is millions to trillions of stars, right? A trillion is a thousand million, or a million million, right? It's a huge number of stars. And you can see that this entire image is packed with galaxies, each of which, as I say, so many stars you couldn't count them in a lifetime. And that patch of sky, it turns out, is typical. This is not an unusual patch of sky. Anywhere you look in the universe, you see a view like this. So that hopefully conveys to you some sense of the enormity of the universe, first of all, the truly staggering number of stars that it contains, and also gives you a sense of what the probabilities might be of finding an object out there like Earth. You may initially think, and a lot of astronomers still do think this, that Earth might actually be genuinely rare. But when I look out at an image like this, and I think of all those trillions upon trillions upon trillions upon trillions of stars, it starts to be hard for me to imagine that among all of them, there isn't some planet out there, at least one, that would be like our own home planet of Earth. Maybe more than one, right? So this is what a lot of astronomers are occupied with these days, trying to figure out where those planets are and learn more about them. But we run into a problem right away when we start this search, which is we have to be very careful to define what we're looking for. It may seem really obvious when we say an Earth-like planet, right? We want an Earth-like planet. We want a planet that maybe we could, live on and walk around on without spacesuits. But that isn't a terribly useful definition for astronomers, because a lot of the aspects of that definition aren't really things that we can measure for planets that are very, very far away. Planets that are hundreds or thousands or more of light years away, right? Very great distances. So we have to be very careful to think about a definition of, what would make a planet Earth-like that is also something that astronomers can actually measure over these vast distances. So when you think about it, maybe pause and take a second. What makes Earth Earth-like, right? What actually makes this planet the lovely place it is for us to live? Well, the most obvious thing you might think of is just life, right? Earth supports life. And so that's a good starting point, right? But the problem is we don't fundamentally actually know what life is. We struggle all the time to come up with a kind of universal definition of what life might be. It's the kind of thing that we know when we see it, but we couldn't necessarily give you a rigorous definition that would allow a machine to say this is life, this is not life. And in any case, most of the things that kind of make up life are, again, kind of tricky things to detect over interstellar distances. So, for example, we might say, okay, the thing that makes Earth Earth-like is the life. The life is based on some common element, and we're going to look for that common element. Well, what's that common element? A logical thing would be to say it's DNA, right? All life that we know of, all life on Earth is in some way based on DNA, right? This fundamental building block molecule that encodes the information that determines what life forms are like on Earth. And that's useful, right? We could certainly say that DNA is in some sense the thing we should be looking for, some planet that has DNA based life on it. But that's hard to do over interstellar distances. We can't easily just sort of pick up DNA on the surface of another planet, many light years away. So we need something else. We need something that gives us a criterion for establishing that a planet is at least in principle like Earth, but also something we have a hope of being able to detect from a large distance away. And if we go back to our photo of Earth, the answer is staring right at us. It's all over this picture. In fact, it's most of what you see in this picture. The answer is water, right? Water is something that marks Earth out as special. Earth has a surface that is, two-thirds water, whereas no other body in our solar system has that same property. So it seems like maybe this is a good starting place to think about criteria that separate Earth like planets from other types of planets. And in fact, this is the criterion that astronomers use. We often have this mantra called follow the water, right? When we look for a planet that might be like our home planet, we look for one that can sustain water on its surface for a long period of time, millions or billions of years. To do that, it's helpful to define something called the habitable zone. So, for any given star, like our own sun, for example, uh, if you put a planet very close to the star, the planet will be very, very hot. If you put it very far from the star, it will be very, very cold, right? But if you put a planet at just the right distance from a star, it can be a nice temperate medium temperature, just like Earth is. And so we refer to this as, the habitable zone. Sometimes it's called the Goldilocks zone because of the story of Goldilocks and the three bears, right? There were the bowls of porridge, one of which was too hot, one of which was too cold, one of which was just right. So in this diagram, the habitable zone is kind of this green shaded ring around the diagram here. So this green area, anywhere in that green area, you could put a planet that was, generally like Earth, and it would be neither too hot nor too cold for water to endure on its surface. So if you took a planet that's reasonably similar to our own planet and you put it anywhere in this green band, you would expect that there could be oceans on the surface of that planet for a long period of time. Now, in our own solar system, if we try and work out where the boundaries of the habitable zone lie, this turns out to be a little bit tricky. You might think it'd be really easy. You can just sort of work out, put a thermometer at different distances from the sun and decide, okay, well, when the thermometer is between 0 and 100 degrees Celsius or something like that, you can have water in its liquid form, right? Below 0, it freezes. Above 100, it boils. So somewhere in there would be good. But it turns out to be a bit more complicated than that because that way of thinking about planets just assumes that the planet's only temperature regulating mechanism is how much light it gets from the star. And that's certainly part of it. A planet has to be warmed by its parent star, or at least it helps to be warmed by a parent star to maintain, a nice temperate environment. But there's more to it than that. So, for example, if we create the habitable zone for our solar system the way I just described, um, it might have, you could arguably put Venus and Mars in it. And yet, neither Venus nor Mars are what we would normally think of as habitable. So, this is Venus, the next planet to the sun from Earth. So, it's a bit closer to the sun. And it's not habitable by any kind of stretch of the imagination, not habitable to life like us, at least on its surface. If you know much about Venus, you'll know it's not a very pleasant place to be. What you see in this image here are the cloud tops of Venus. The entire planet is perpetually shrouded in thick clouds, and in fact, it has a very thick atmosphere. So, what does this atmosphere have to do with its habitability? Its ability to sustain life? Well, if we contrast Venus with Earth, we see a number of very striking differences. So, first of all, on Earth, the average surface temperature is about 15 degrees Celsius. Obviously, colder at the poles, warmer at the equator, but on average, it's about 15. On Venus, it's 460 degrees Celsius pretty much everywhere on the planet, pretty much all the time. It's horrible, right? No known form of life could endure at those temperatures indefinitely. So, why is that? Even though it's a bit closer to the sun, that alone doesn't explain this boiling hot temperature. Well, the next two properties help. So, on Earth, if we define the thickness of our atmosphere, the atmospheric pressure, we call that one atmosphere, right? What you're feeling right now, assuming you're close to sea level, this pressure on your body, this amount of gas in the room with you, that's one atmosphere of gas. On Venus, if you were to stand on the surface, you'd feel 92 atmospheres. So you would literally feel the atmosphere squeezing you a bit. And a big difference is that on Earth, of that one atmosphere, a tiny, tiny, tiny amount of it is carbon dioxide. And as you hopefully know, carbon dioxide is a very powerful greenhouse gas. It's the gas that we as human beings are continually adding to Earth's atmosphere, which is what is driving warming of our planet. This is the kind of thing we're trying to prevent. And at the current time, our own atmosphere has about 0.04% carbon dioxide, whereas the atmosphere of Venus is almost entirely carbon dioxide, 96% carbon dioxide. So it's 96% carbon dioxide, and there's way more of it. And that means that Venus has an immensely powerful greenhouse effect, so strong that instead of it being, a nice temperate 15 degrees, it's 460 degrees. It's literally the temperature of a hot oven because of this powerful greenhouse effect. So very few spacecraft have ever landed on the surface of Venus, but here's one of the ones that did. This is from a Soviet spacecraft called Venera. Um, and this was decades ago. It landed on Venus, and you can see it's not a very Earth-like kind of environment, right? It's this kind of blasted rock with certainly no obvious evidence of life, and we wouldn't expect any at that temperature. So, what if we go the other direction from the sun and we look at Mars? Could Mars be an Earth-like planet? Well, at first glance, it looks very different from both Earth and Venus. It doesn't have that thick layer of clouds, but it also doesn't have oceans. We can see clear to the surface, no problem, quite different from Venus, but there are no oceans there. And again, the explanation for why this is has to do with its atmosphere. So, just as Earth has a kind of moderately thick atmosphere with a small amount of greenhouse gases, which keeps it nice and warm, Mars has much less atmosphere, almost no atmosphere, right? It's got a very thin, thin, thin little atmosphere. You can see here it's 0.006 atmospheres. So a fraction of a percent of Earth's atmosphere. But again, like Venus, that atmosphere is 96% carbon dioxide, which helps warm Mars up a little bit, but given that there's so little atmosphere overall, it doesn't help enough. So the average temperature on Mars is about minus 60 degrees. And that means that water can't endure in a liquid state for long periods of time. Due to various factors you can ask me about later if you're interested, in the history of Mars, it's also lost a lot of the atmosphere and the water that it once had, which means that in the present day, Mars is basically a cold desert. Right? If you look at it, this is a photo taken from the surface of Mars. It doesn't look too inhospitable. It's not as bad as Venus for sure. You could live there if you had the right equipment with you, some oxygen, a good winter coat, things like that. But it's not obviously habitable to life in uh, the same sense that Earth is. There isn't a lot of liquid water hanging around to support life. There doesn't seem to be much life on the surface. If there's any at all, it's probably microbes below the surface, maybe. So not obviously habitable. That said, we do know that Mars has water. It's just that that water is frozen. So all over the surface of Mars, there are deposits of frozen water. You can see water mixed with carbon dioxide, frozen into the bottoms of craters. We can detect it in the soil on Mars, and we know that there is water there. So actually, if you reverse course and you go back in time and imagine what Mars would have been like a long time ago, we know Mars did once have an ocean, not a very thick ocean, but it did have an ocean, and therefore may have been habitable. Maybe it was able to support life, but not anymore. So that's a key thing to keep in mind when we think about an Earth like planet. Some planets can be Earth like, but not for very long. And certainly Mars was once Earth like. Maybe Venus was once Earth like, but only Earth itself has kept that nice habitable environment for billions of years. So that pretty much exhausts the possibilities in our solar system, right? Beyond that, we have Mercury, it's too close to the sun. And then we have the gas giants, which don't even have a solid surface. So kind of hard to characterize them as Earth like in any sense. So that's when we turn to other solar systems and we start to ask about these so called exoplanets. So, exoplanets are planets that orbit stars other than the sun, right? So, we have 8 planets orbiting our own sun, and then many, many more planets orbiting other stars. Now, what's exciting about this area of astronomy, exoplanet science, is that it's developing incredibly rapidly. In the early 1990s, the total number of confirmed exoplanets orbiting stars that were kind of like the sun was zero. None of them known. For literally thousands of years prior to this, people had speculated that there might be such planets, but due to limitations of our technology, we hadn't actually found any. Now, in the mid 90s, 3 exoplanets, 3 planets orbiting stars other than the sun, were detected, orbiting stars that are kind of similar to the sun in some sense. But these were not even close to Earth like. These were what we call super Jupiter planets or Jovian planets. These are planets that are big gas giants like Jupiter. So they may have a tiny rocky core buried deep, deep, deep in the center, but the majority of their volume is liquid hydrogen, which not very habitable, right? I don't know about you. I can't survive in an ocean of liquid hydrogen. And then beyond that, they have a thick layer of gas. So not even close to Earth like. And then we keep going. By the year 2000, there were 55 exoplanets known, and those again were basically all Jupiter style planets, big gas giant types of planets. 10 years later, 591 exoplanets known, and they're getting smaller and smaller. As our techniques got better and better, we were able to detect smaller and smaller planets. But we're still here at this point, mostly in gas giant territory. We're getting into sort of Uranus and Neptune territory. We sometimes call those ice giants. But the point is, they don't have a conventional solid surface the way little rocky planets like Earth do. As of 2022, we know of 4,900 and change exoplanets. And now we do actually know of lots of Earth size and smaller exoplanets. So only in the last really decade have we been able to actually identify planets outside our solar system that were comparable to Earth in size and therefore potentially Earth like. Now, maybe some of you, maybe many of you know how we actually go about finding these planets, but for those who don't, it may not be the way you think. You might naturally think if you want to find a planet elsewhere in the universe, you point a telescope and you look, right? That makes sense. That is absolutely what we would most like to do, but it's incredibly challenging. It doesn't usually work. That method of just look at a star, look for planets. It has worked a few times, and people are still working on that technique. Here's what it looks like when it does work. So this is a little movie of, and it just repeats. What you see here in the center of this image, you see a little yellow icon of a star. And then there's all this kind of junk around it, all this kind of fuzzy flashing lights. But I want you to focus on these four dots. Those are planets orbiting in another solar system. Now, to get this image requires a lot of technological trickery, not trickery, but technological techniques. So basically, the problem you're facing is that if you want to look at another star and see its planets in an image like this, the big problem is the star. It's like staring into the beam of a stadium light and trying to take a picture of a firefly, right? The stadium light is just blinding. If you literally try to do that, take your camera, take a picture of a stadium light, and there's a little firefly sitting on the stadium light, there's no hope you're going to see the firefly. The stadium lights blind you. So that's what happens when we try to take pictures of planets orbiting other stars. The stars blind us. In a small number of cases, we can do some technological trickery. Basically, we kind of block the star with an actual dot in the telescope, and then a lot of digital work, right, to sort of digitally process the image and get rid of the light of the star. And that's why you see all this kind of background remnants of subtracting the star from the image. But lo and behold, you can actually see planets. Now, our topic today is the search for Earth like planets, and these are not Earth like, not even a little bit. The only planets you can see using this method are gigantic Jupiter sized planets, and they are bigger, and they have to be quite young. Because when they're young, they're hot and they actually glow a bit, which helps us see them. And they have to be really far from their parent stars. So, not even a little bit Earth like. Okay, so when we do find Earth like planets, how do we find them? Well, that relies on a variety of other methods, but in particular, this one method we call the transit method. So, in this method, if I can get my little video to play. In this method, basically what you do is you stare at a star for a long time, literally years, and you wait for a planet to pass in front of the star. Now, in the video, you're actually seeing this. You're seeing the circle of the star, and you're seeing the planet cross in front of it. This is not what we actually see. What we actually see is the little graph in the bottom left. So what we do is we measure the brightness of the star. We take a picture, measure the brightness. Take a picture, measure the brightness. Take a picture, measure the brightness, and just do that, every minute for years. And if there's a planet orbiting that star, then every time the planet passes in front of the star from our perspective, it blocks some of the light from the star. And so instead of this nice, steady, 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 light output from the star, here comes the planet. It's going to pass in front of the star, and the graph is going to dip right there. Right where the planet passes in front of the star, you lose a bit of the light from the star, and then you regain it when the planet passes across the star again. So we call this the transit method. Every time a planet passes in front of a star, we call that a transit. And using this method, we've been able to identify most of those planets I mentioned to you earlier. That's how most of them have been found, thousands and thousands of planets. One of the really nice things about this method is that it right away gives us a measurement of the size of the planet, because a bigger planet will produce a deeper dip in what we call this light curve here. So if you had a Jupiter-sized planet, it would block more light and the dip would be deeper. If you have an Earth-sized planet, it's a smaller dip. And by measuring the size of the dip, you can work out the size of the planet. So this is really useful because this allows us to decide whether the planets we're detecting are, gas giants, or are they terrestrial, meaning Earth-like planets, right? So here is a snapshot of some of the systems that have been found using this method. So on the bottom is a graphic of our own solar system with the sun at the center. And then the blue circles correspond to the orbits of Mercury, Venus, Earth, and Mars. The green shaded area is that habitable zone, right? That's the area a planet that was like Earth would have to be in for it to be able to maintain water on its surface for a long time. And you can see again, Venus is kind of sort of on the edge of that. Mars is sort of on the other edge of that. Only Earth is firmly in the middle. Now, in this kind of middle system here, this is the Kepler 452 system. And the Kepler 452 star is a lot like the sun, and it has a habitable zone that's a lot like our habitable zone. And lo and behold, in that habitable zone, there is a planet orbiting called Kepler 452b. And Kepler 452b, this is an artist representation of it. We remember we don't actually see the planet, we just see the way it blocks light from the star. You can see here it's shown to scale with Earth. So Earth is this size and Kepler 452 is this size. So we would call this planet a super Earth. And actually, we don't know yet whether super Earth planets could be habitable. It's possible they are. It's also really possible that they're not. They might have very thick atmospheres like Venus. They might have enormously thick oceans, which make them, quite different from Earth-like planets. So we're not totally sure yet. But up here at the top is a very different kind of solar system. So this is the Kepler 186 system. And the star in this system is a small dim star, much dimmer than our sun. You'll also notice it's a bit redder. This is a kind of star called a red dwarf. And because it's a dim star, not as hot, not producing as much energy, the habitable zone is closer to the star. It has to kind of hug the star to stay warm, right? So it's sort of the difference between, being next to a roaring campfire versus, someone holding up a cigarette lighter or something like that, right? This would be, a tiny, tiny little bit of warmth. You have to be very close to it. So the Kepler 186 system has a planet called Kepler 186f, which is very similar in size to Earth. So these are the kinds of planets we're finding these days that raise our hopes that we may be, close to finding a planet that is quite similar to Earth. I could show you these all night. There are lots of them known now. This is a very recently detected one from a different satellite. These previous ones were from the Kepler Space Telescope. This one is from a telescope called TESS, the Transiting Exoplanet Survey Telescope. I think that should be Survey. I forget actually what the other S is, but in any case, TESS. So TESS has found an Earth-sized planet orbiting in the habitable zone of a star. So here again is the habitable zone. And this planet called TOI, TESS Object of Interest 700d. Again, this is an artist's impression of it, but it's a sort of roughly Earth-sized planet. It's a tiny bit bigger than Earth, and it orbits in the habitable zone. One thing that's exciting about this system is it's only 100 light years from Earth. So 100 light years is quite far. We don't have any technology capable of traveling that far yet, but it's close enough that our telescopes can help us get a clearer sense of what this planet might be like. And I'll come back to that in a moment. Okay, here's another system that many of you may have heard of. This is the TRAPPIST-1 system. This system is, a lot of people are deeply in love with this system. It has 7 known planets. 3 of those planets orbit within its habitable zone, and they're all sort of approximately the same size as Earth. So 3 planets in the habitable zone, and it's only 40 light years from Earth, 40 light years. So that's really close. That's about as close as we could hope for a system like this. There aren't a lot of other options that are much closer. So we're really starting to pile up these planets now, planets that are in the habitable zone and that are similar in size to Earth. Now, this is a kind of a representation made by some astronomers at the University of Puerto Rico, and they update this all the time. This is the list of the most habitable exoplanets ranked by distance from Earth. So you can see the very nearest one is actually orbiting the very nearest star to our sun, which is called Proxima Centauri. And then they go out to more than 1,000 light years away. So we're constantly finding new potentially habitable planets, and there are about a few dozen of them known now that could be Earth-like. However, remember that the main thing that distinguishes, some rock that is in the habitable zone from a genuinely Earth-like planet is its atmosphere. And with this transit method, we don't find out about the atmosphere usually. We find out how big the planet is. So that allows us to tell whether it's a Jupiter type planet or an Earth type planet, but it doesn't tell us whether it's an Earth type planet or a Venus type planet, right? Earth and Venus are almost the same size, but it's the atmosphere that makes the crucial difference between them. If we could put a nice Earth like atmosphere on Venus, it would be a lot more Earth like. Similarly, if you put a Venus like atmosphere on Earth, it would be a horrible, horrible place. So, to truly understand whether any of these potentially habitable planets are actually Earth like, we need to know about their atmospheres. And for the most part, that has been not possible with the technology we have in hand. To figure out what an exoplanet's atmosphere is like is an enormously technologically challenging thing to do and a really time intensive thing to do. You need a ton of time on a powerful telescope to do this. Luckily, there's a new telescope on the scene. This is the James Webb Space Telescope. Many of you may have heard of this one. This one went up late last year, and it is a general purpose telescope like the Hubble Space Telescope. It's meant to do a whole bunch of different kinds of science. But one of the things that it's capable of doing is uh, looking at exoplanets and measuring the chemical composition of their atmosphere. So this is going to be absolutely crucial. This is going to start to tell us which of those potentially habitable planets is actually habitable, which ones have thick carbon dioxide atmospheres like Venus, and which ones have thinner nitrogen oxygen atmospheres like Earth. So that's going to be a huge revolution, right? In the next 5 years, you're going to start hearing more about uh, the actual atmospheres of some of these near Earth exoplanets, and we're really going to start to get a sense of which ones might actually, not only be able to host life, but we might even start to figure out which ones do host life. Okay, so that's we've kind of covered two parts of this search for another Earth, right? We've talked about planets in our own solar system, but we've also talked about planets in other solar systems. But here's the thing. When we talk about looking for another Earth, what we're really talking about is looking for some place where life could exist, right? I think that's fundamentally what we want, right? We want a planet or a place where life could actually exist. Life that's like us, ideally. It would be nice to find life that was unlike us. That'd be amazing. But for the purposes of, kind of going out and exploring the universe, we'd like to know that there are some places where we could survive or life like us could survive. So, with that in mind, I want to suggest to you that we might be a bit mistaken in placing all of our emphasis on planets. Because if we look even in our own solar system, we find that many of the places that satisfy our criteria for habitability, for ability to sustain life, aren't planets. We think often, when we think about another Earth, we just assume Earth is a planet. This has got to be a planet, right? Where else would we live? But what if we're wrong? So here is a composite image of all of the round things in our solar system that aren't the sun. And you can see they're not all equally round. Some are more round than others, but these are round things in our solar system. And they're not labeled. Now, if you know a bit about astronomy, you can probably start to pick out which objects some of these are. But what I challenge you to do, if you don't know what they are already, is decide which ones are planets. Some of them are, but which ones? The point is, you can't tell just by looking at them. Our definition of what a planet is depends in large part on where it is. So our fundamental component of our definition of a planet is that it orbits a star. But if you took exactly the same object and put it in orbit around a planet, so a planet orbiting a planet, we stop calling it a planet. and we call it a moon. Even if it was exactly the same object, right? There's no reason, if we literally took Earth and put it in orbit around Jupiter, we would call it a moon. We wouldn't call it a planet anymore. So if I reveal to you which ones of these are planets and which ones are moons, the answers might surprise you. So the very first one here, this is Mars. It's a planet. The next one, the next biggest one, is a moon. This is a moon of Jupiter called Ganymede. The next biggest one is also a moon. This is a moon of Saturn called Titan. And then the next biggest one is a planet again. That's Mercury. So what's interesting about this is, again, if I took Titan and I put it in orbit around the sun, you would just obviously call it a planet. It would satisfy all your normal criteria of being a planet. But because it orbits Saturn, we call it a moon, and therefore we forget about it when we think about where to look for habitable environments. But this is a mistake, and here's why. This is a photograph, a sort of overexposed photograph of a moon of Saturn. So what you see in the background here, these bright lines, those are the rings of Saturn. This is kind of a close-up photo of this moon taken by a spacecraft orbiting in the Saturn system. And this silhouette here, big circle in the foreground, this is the moon. It's a moon called Enceladus. And at the bottom of this moon, hopefully you can see there are these plumes, these kind of sprays or jets of something coming out of this moon. And those jets are jets of water. All this time we've spent talking about, hoping to find water because water is this essential ingredient for all life as we know it. And we say, well, Mars doesn't have it, Venus doesn't have it, Mercury doesn't have it, but Enceladus does, right? And that's in our own solar system. We don't need to go to another solar system. In fact, Enceladus is not the only such object. There are several moons of both Jupiter and Saturn that are known to have subsurface oceans. Now, it's that subsurface part that makes them not exactly Earth-like in the conventional sense. They do have oceans. In fact, some of these moons may have more liquid water inside them than the oceans of Earth, but it's underneath a layer of ice. So it's a different kind of a system. These moons are kept liquid in their interiors not by sunlight, right? Their surfaces are freezing cold because they're so far from the sun. So they have really thick layers of ice, kilometers of ice. But underneath that, the interiors are kept liquid by gravitational interactions with the planets they orbit. It's essentially the same phenomenon as tides on Earth, right? The moon raises tides in the Earth's oceans. These planets' gravity raise tides inside their moons, and the tides cause the moons to kind of flex and stretch in a way that creates heat, and that keeps the interiors liquid. In fact, there are even signs that some of these oceans might have hydrothermal vents. These are we have these on Earth, right? We have these vents at the bottom of the ocean where boiling hot water bubbles up from the interior. And these are thought to potentially have been where life on Earth first formed at these hydrothermal vents. We don't know that for sure, but it's a not a bad guess so far. We believe there may be these hydrothermal vents on some of these moons. And if that's true, and that's where life came from on Earth, maybe they already have life buried under these thick layers of ice. Now, to try and work that out and decide whether these moons actually might be our most promising candidates for places to look for life, there will be spacecraft on their way to them soon, or to some of them. So in the past, we've sent spacecraft to both Jupiter and Saturn, but they've sort of, flown around and done general purpose things looking at all the different parts of the system, right? Each of these planets has about 60 moons or more, and they've been sort of all examined a bit. But there are two new spacecraft going to two different moons of Jupiter, one called JUICE, the Jupiter Icy Moons Explorer, and it's going to go to Ganymede, this largest moon in the solar system, which has, as far as we can tell, an ocean under its ice. And the other is called Europa Clipper. It's going to go to Europa, which is another moon of Jupiter that also has a subsurface ocean. So those are two spacecraft. They're both going to launch in the next few years, and they will both arrive in the early 2030s. And both of them are going to study from orbit the interiors of these moons and try and tell us more about those subsurface oceans and what might be in them. So that's going to be really exciting. It's going to be a bit of a wait, early 2030s, but it's going to be very exciting. So what does the future hold? for the search for Earth-like planets? Well, this is a timeline showing some of the major telescopes that have been involved in this search so far. So the Hubble Space Telescope and Spitzer Space Telescope. There's a European mission called Corot, which has successfully found some exoplanets. The first big dedicated exoplanet finding telescope was the Kepler Space Telescope. That went up in 2009 and has since kind of run its course and is done now. That one found a large fraction of the planets we know so far. There's now the Gaia mission. Gaia is it's doing a variety of things, but one of the things it's capable of doing is finding a lot of exoplanets. It's probably already found thousands of them, but the data are still being analyzed. That will be coming out within the next year or two. Currently, the TESS satellite is up, and it's doing something very similar to Kepler, a slightly different strategy. But then we have a whole bunch more of these satellites coming up. There are two on here that I think I've already mentioned Webb. There are two on here that I think will be very, very exciting. Plato and Ariel. These two are going to search for and characterize Earth-sized planets orbiting nearby sun-like stars. That's kind of the idea, right? So they will look for planets that are in solar systems fairly similar to our own, and they will try and tell us something about the atmospheres of those planets in the hope of telling us not only whether they are capable of hosting life, but in some cases, it may even be possible to decide whether they do host life, which would be incredible. Totally revolutionary discovery. Okay, so just before I wrap up, I want to point out that this is, this effort, you can see all these satellites and everything, they consume an enormous amount of attention of astronomers, right? This is a huge industry now looking for exoplanets and trying to find a planet that might be capable of supporting life or even does support life, right? But there is a shortcut, right? There's a way to do this that is much, much, much easier and doesn't require, space telescopes and all of this kind of fancy equipment that costs a lot of money, but it only works in a very narrow range of cases. And that method is if there is an Earth-like planet out there with Earth-like creatures on it. If there are planets out there that have intelligent life on them, we may be able to identify them simply by attempting to communicate with the life that they host. So, of course, in parallel to all of these other missions to find the planets themselves and characterize them, we also spend part of our time as astronomers trying to be ready should any of these planets be signaling to us and attempting to demonstrate that they do, in fact, host life and, in fact, intelligent life. Okay, so that has been a quick tour through what is going on these days in the search for another Earth-like planet elsewhere in the universe. I hope that has been informative and entertaining, and I would very much love to answer any questions you may have tonight. Thank you so much.
Thank you so much, Dr. Reid, for leading us through this exploration of planets beyond our solar system. We are going to check in now with RASC DDO Outreach Coordinator, Quentin Wayrich, who has been monitoring the YouTube chat for questions from our viewers. Quentin?
Hey, we do have quite a few questions from chat today. So thank you once again, Dr. Reid. What an excellent talk. Our first question is from Eric Briggs, who asks, what's your favorite extrasolar planet and why?
My favorite extrasolar planet is, it changes pretty often. I would say right now it's probably the Proxima b. So Proxima is the nearest star to our solar system. And I mean, it would be my favorite, not because it's the most likely to be habitable, it's probably not, but because it's so close, right? It's so incredibly tantalizingly close that there's even a chance that within my lifetime we could send spacecraft there if we really got on it as soon as possible. We could send very, very tiny spacecraft to that system and get some close-up images, but we will certainly be able to study it with some of the the coming generation of super duper telescopes and learn more about it. It'll just be easier to learn about than others, so that's one reason it's probably my favorite.
That'd be really exciting. the possibility of sending a space probe to another star system. That's incredible. I have a question here from Zapfan. Any answers on what is blocking the light of Tabby's star? Are you familiar with Tabby's star?
Yeah, so Tabby star is one of a couple of objects where, so this method that I described to you, this transit method, right? In the video I showed you, I'll put it up again. So the way the method works is, let me just go back to get the video started. The way the method works again is you monitor the brightness of the star and you look for dips, okay? But these dips are very brief and they're very shallow, right? They block it like, it's a tiny, tiny, tiny dip. This graph vastly exaggerates how deep the dip is. It's, it's like a less than 1%, much less than 1% typically. In a couple of cases, including Tabby star, these graphs, we call them light curves. It looks totally different. There are huge dips in the light curve, as though something gigantic is passing in front of the star, right? And it doesn't follow the same pattern as an orbiting planet does. And so this has led to all sorts of speculation about what these kinds of things might be. And most of those explanations involve various kinds of debris around the star. So we don't usually think of solar systems as being full of junk, but they are. Our own solar system is reasonably clear of junk, but a lot of solar systems are not. So we have an asteroid belt and a Kuiper belt. These are kind of repositories of asteroids and comets in our solar system. In some other solar systems, they have much bigger bands of debris, and some of that debris is in little tiny pieces and things that are pretty effective at blocking light. So it seems like in these cases where you wind up with these greatly distorted light curves that suggest something gigantic is in the way, that it's some kind of debris cloud in that solar system typically.
I see. So you suspect that Tabby star's interesting behavior is caused by a debris cloud of some kind.
I think probably. I think the jury is still a little bit out on that. People still argue about it. Could it be something to do with the star? Could it be? I mean, a tiny, 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 tiny minority of people wonder whether these are attempts by extraterrestrials to communicate with us by putting things in orbit around stars to produce weird light curves that we might notice. But most of I think the general consensus is that the explanation is natural, and it's just that there's other stuff orbiting the star.
I see. Thank you. I have another question here. Are extrasolar planet candidates mostly going to be confirmed later, or how many of them are probably false positives? And this is also from Eric.
Right. So a lot of them, there are way more candidates than there are actually confirmed ones. So the numbers that I quoted to you earlier were confirmed. And usually a confirmation involves, repeated observations, right? Someone has gone through and observed the same planet many times, or used multiple telescopes to observe the planet, or ideally used multiple different methods. There are about 6 or 7 methods now that you can use to detect various kinds of exoplanets. And so it's always nice when you can use more than one method to independently confirm the planet. So I said there were less than 5,000 confirmed ones. There are, at this point, depending on whose data set you happen to have access to, there are probably tens of thousands of candidate exoplanets. So, but they slowly get confirmed over time.
Okay, so that makes sense. Obviously, you want to independently confirm these through as many different methods as possible. That's more scientific, right? Just to yeah. Now, I have a question of my own that I'd like to ask you if that'd be okay.
Of course.
So if we found an exoplanet that met all of the criteria for habitability that we are able to test for, so we have like a very, very good candidate for a habitable exoplanet, what do you think our next step should be? Would you want us to send a probe there?
Well, depends on exactly how much you learn about it, right? So with all of the telescopes that I have described to you so far, what you could mostly learn is kind of bulk properties of the atmosphere, right? So you can learn basically the kinds of things that I've told you about, Mars and Venus. Like it's this percentage carbon dioxide, it's this much atmosphere in total, that kind of thing. That's the kind of thing we're going to learn from the telescopes that I've mentioned so far. But there's a whole other generation of telescopes that have yet to be kind of confirmed. So I don't have names for them and things. They're just sort of always on the drawing board. And those would be something called interferometer based telescopes, right? We have this kind of telescope on the ground, but to do this for exoplanets, they have to be in space. So the idea is, instead of having one giant telescope, you have a constellation of telescopes, right? And they spread out over a large volume of space, and they all look at the same planet. And by digitally combining the different perspectives that they each you can kind of chain them together so that they give you a clearer view than certainly any one of those telescopes could get. But they give you a view that's as if you had a colossally gigantic telescope. You could get a telescope the size of the orbit of the Earth or something, and with a telescope like that, or even a much smaller version, you'd be able to actually see the surfaces of these planets, right? So without even having to send a probe there and wait, decades or centuries or whatever for it to get there, you'd be able to image the surfaces of these planets. So that's what I would want to do. I think that's what a lot of people are hoping for. There have been a number of these types of telescopes proposed in the past, and they've always been shelved because the technology that we would need just isn't there yet, but we're getting really close. I think, probably within a decade, there'll be a firm proposal to build one of these space interferometers, and that will allow us to actually start seeing, pictures of the surfaces of these planets, which will be crazy exciting, right? Imagine what you might see. You could see continents. You could see, what if you see green on the continents, some forests, or what if you see lights on the continents on the night side, right? Oh, is there cities there, right? So there's still loads we could learn without having to actually try and go there, which would be enormously expensive.
Yeah, Zapfan just said terrestrial planet finder needs to get built, and I could not agree more. That sounds incredible.
Exactly, yeah.
So,
terrestrial planet finder is one of these concepts for a space interferometer that has been sort of permanently or repeatedly shelved, right? Just because, as they say, the technology is not quite there yet. But I think we will have the technology relatively soon.
That's awesome. Okay, well, I believe that concludes all of our questions from the chat. Thank you so much, Dr. Reid, for talking with us tonight.
You're very welcome. Thank you so much for having me. I hope everyone had a good time, and stay safe and keep looking up.
Absolutely.
Thank you so much, Quentin, for relaying those great questions. And Dr. Reid, amazing answers. Thank you for giving us all of those incredible details. We have learned a lot tonight about planets outside of our solar system and about planets in our solar system. But we do have a little bit more on our program this evening. This is a DDO online event, and so of course we have a tour of the DDO. We have a short video for you here with a quick tour introducing the telescope and the facility. We will come back after this video to answer any questions you might have about the DDO facility or the telescope itself.
Hello and welcome to the David Dunlap Observatory. Behind me is Canada's largest optical telescope. My name is Denise Chilton, and I am a rascal, a member of the Royal Astronomical Society of Canada, Toronto Centre. It is my pleasure to be an operator for this telescope, and tonight I'm going to give you an inside look at this telescope and how it works. But first, let's think about the history of this scope. This facility opened in 1935. Originally, it was a research telescope for the University of Toronto. It was named in memory of David Dunlap, who had thought that he was going to provide some funding for the construction of this scope, but his unfortunate death prior to that funding being secured put the future of the scope in jeopardy. It's very lucky that his widow, Jessie Dunlap, came forward to donate the funds for this facility. The telescope was built by Grubb Parsons in England, in Newcastle on Tyne, in 1932 and 1933. It was shipped across the Atlantic in pieces after being completely built and assembled and then disassembled in England. It was shipped here and rebuilt on this site, and it opened in 1935. It was in use as a research telescope for many years, but unfortunately, due to light pollution and the availability of bigger and better research telescope facilities, the University of Toronto closed this telescope in 2008, and the property was eventually sold to the city of Richmond Hill. The good news is that the telescope is now open for public tours. Unfortunately, with COVID, we can't have people in the building, but tonight it will be my pleasure to show you how this telescope works. So how does a telescope work? Well, a telescope points outside at the night sky. Light flows down the optical tube, light from moon or stars or planets or dark sky objects, and it's collected by the great big mirror behind me. This is the primary mirror in the telescope. In this case, this one is 74 inches across, or 1.88 meters. You can probably see my reflection back there behind me, and it's this diameter that makes this telescope so powerful at collecting light and at being able to see very distant objects. When this facility opened in 1935, this became Canada's largest optical telescope, taking that record from the Dominion Astrophysical Observatory in Victoria, British Columbia. Their mirror is only 72 inches in diameter. Rumor has it that when Dr. Clarence Chant, who commissioned this telescope, placed the order for this mirror, he asked specifically for it to be 2 inches bigger than the Dominion Astrophysical Observatory's telescope mirror, so that he could have the record of the largest telescope in Canada. When this opened, it was also the second largest telescope in the world. No longer the case, of course, as much larger optical telescopes have been created since then. To get back to how a telescope works, light flows in from the night sky outside and is collected by this great big primary mirror and bounced back in that direction toward you. I'm not sure if you can see this contraption at the top end of the telescope here. This is the secondary mirror attached to these vanes. The secondary mirror collects the light from this primary mirror and sends it back down the telescope to the hole in the very center of the mirror. This hole leads to an eyepiece down below, and that's where you, if you were here, could come and look through the telescope and see distant planets, distant stars, or dark sky objects. You might have noticed that the sun rises in the east and sets in the west. If you were to stay up all night, you might notice that all of the objects in the night sky do the same. The moon, the stars, the planets, and more. This is because the Earth is rotating. But what this means is that the telescope needs to be able to lock on to night sky objects and then track them across the sky as the Earth rotates. So we have some controls over here that allow us to lock onto our targets. Every object in the night sky has a set of coordinates. We call these coordinates right ascension, for east to west, and declination, for north to south. These are the same as latitude and longitude coordinates for objects on Earth. Let me show you how our controllers work. This is our declination controller. It helps the telescope move north to south. Let's watch how that works. As the telescope is moving north, we can see the coordinates in the counterweight on the other side of the telescope, so we know exactly where it's pointed. Now that we have our declination coordinates locked in, north to south, we're going to lock in our right ascension coordinates, east to west. We use this wheel to do that. First, we unlock the telescope. And then we can turn the wheel. And our coordinate system is up here on the setting circle so that you can see where the telescope is pointing exactly. And we turn the wheel until it's pointing in the right direction. Once the telescope is pointed in the correct direction, we need to lock it in place again so that it doesn't swing around. But you might have noticed that the telescope is no longer pointing at the open sky. Instead, it's pointing at the inside of the dome. So we need to rotate the dome roof to bring the open window in front of the end of the telescope. The dome weighs 80 tons. It rotates on a set of 24 train wheels connected to a cable and pulley system powered by a motor downstairs. Once the open shutters are in position, we're ready to start observing the night sky. Just up this ladder, we can find our way to the eyepiece. I wonder what I'll see tonight. Thanks for joining us for this virtual tour of the David Dunlap Observatory. We hope to see you here in person as soon as we're able to reopen the facility for public tours. Until then, wishing you clear skies.
I hope you enjoyed that tour of the DDO facility and that this glimpse inspires you to visit the telescope and its buildings to learn more about the facility and its rich research history. The facility is in the process of slowly reopening to the public as pandemic restrictions continue to ease, and we will continue offering live streams like these for a while longer. If this tour is not yet enough to pique your interest in visiting the DDO, let's take a quick look now at a view through the 74-inch or 1.88 meter telescope at the observatory. So coming up on your screen, you should be seeing an image of Jupiter. This is, of course, the largest planet in our solar system. Its mass is more than 2.5 times the mass of all of the other planets in our solar system combined. So through the big telescope, we can see this planet as a disk. To help understand the scale of the planet, we could fit 11 Earth diameters into the diameter of the planet Jupiter. Jupiter is called a gas giant because it is composed predominantly of hydrogen and helium gases. Unlike the terrestrial planets of the inner solar system, it does not have a rocky surface. What we see of the planet are the cloud bands formed by weather patterns in the upper atmosphere. You might be familiar with the planet's Great Red Spot. This has been observed on the planet in the planet's atmosphere for at least 400 years, first observed by Galileo. Photographs taken throughout the 20th century show that the Great Red Spot is in fact shrinking. Nevertheless, the diameter of this massive storm is still wider than that of our home planet, the Earth. While Jupiter has no rocky surface, the core of the planet, if you will, is gas compressed by the pressure of the planet's enormous gravity into a fluid. So let's go back now over to our outreach coordinator, Quentin Wayrich, to check in. Are there any questions about the David Dunlap Observatory?
There do not appear to be any more questions from the chat about the David Dunlap Observatory. Thank you.
Okay, perfect. Thank you so much, Quentin. On behalf of the Royal Astronomical Society of Canada Toronto Centre and the RASC DDO Committee, I'd like to thank Dr. Michael Reid once again for sharing this incredible glimpse into our cosmos with us tonight. Thanks also to our technical support team, Andrew Reid, Elizabeth Reid, and Ward LeGros. Thanks especially to Quentin Wayrich for fielding all of those wonderful questions from you, our YouTube audience. And so, of course, thank you, our viewers, for joining us this evening. This talk is part of our 2022 season of astronomy events at the David Dunlap Observatory online, offered through the partnership of the Royal Astronomical Society of Canada Toronto Centre and the City of Richmond Hill. Our upcoming events include an Up in the Sky event on April 23rd. This is a sort of star party where we hopefully have live views through the big telescope at the DDO and live views through some member telescopes as well, some smaller telescopes. So I hope you'll join us for that. On April 24th, Sunday, and on May 8th, we also have 2 Sunday sun gazing events coming up. So similar to the Up in the Sky event, which looks at nighttime targets, the Sunday sun gazing events focus, of course, on the sun. So these are daytime observing events where we point our telescopes with all of our special safety filters at the sun and give you information about what you're seeing and how the sun works. We have another speakers night coming up on May 13th. We have Nassim Borzonia, who will speak about dark matter. And we have Ask an Astronomer coming up on May 15th. This is your opportunity to get online with one of our DDO astronomers and ask all of your burning questions about astronomy. All of these events and more are posted on our website. That's rascto.ca. So please do have a look there for more details. Now, if you're excited about getting started in astronomy for yourself after tonight's event, we will be wrapping up this evening with a short video with some quick tips for how to get your astronomy observing hobby going. So please enjoy this video, and wishing you a wonderful night, a great weekend, and clear spring skies. A question we're often asked is, how do I get started in astronomy? It's a really great hobby, especially in this COVID context. It gets you outside for fresh air, you don't need to do it in a group, and there are tons of free resources online. So here's a quick guide to getting started in astronomy. Step 1 is to learn the sky. This really is essential, as it's important to be able to orient yourself and know what you're looking at. There are lots of resources to help you with this. If you prefer books, I can recommend Night Watch by Terence Dickinson or The Beginner's Observing Guide by Leo and Reid. Or if you'd like to print out some star maps and star finders, there is the star finder from the Royal Astronomical Society of Canada. That's a printable star finder that you can take out with you under the night sky. Or you can print sky maps and sky atlases from skymaps.com. If you're a little more tech savvy and you prefer programs and apps, I recommend Stellarium. This is free planetarium software you can install on your home computer. Or Sky Safari. This is an excellent app for your phone. Once you've got your bearings, step 2 is to start observing. That's right, just head out under the night sky and look up. You don't need any special equipment, just your eyes. With your eyes, you can see things like constellations and asterisms. These are the formal and informal patterns that stars make in the night sky. You can see planets like Mars and several other planets as well. You can see the moon and observe its different phases as it moves across the sky. You can see meteor showers, comets, and even one galaxy that's bright enough to see with your naked eyes in a very dark sky area. Maybe you're inspired to look for more than what you can just see with your naked eyes. So step 3 is it's time to start collecting some gear. Now, you might be surprised that you may already have some of the things you need lying around the house. If you have a pair of binoculars, you can point those at the stars. If you don't, they're a small investment with a lot of benefits. With binoculars, you can see details like craters on the moon, or the phases of Venus and the moons of the planet Jupiter. You can even see smaller, fainter asterisms and double stars. Remember, one of our famous astronomers in history, Galileo, started out by using a telescope that didn't have much more magnifying power than an average pair of binoculars. His contributions to astronomy are remarkable, and you can see a lot through your binoculars too. If you're ready to get a little more serious about your astronomy hobby, you might consider investing in a telescope. A small amateur telescope is a big investment, but with more magnification possible, you can see more detail on the surface of planets, the moon's craters, you can see many double stars, some galaxies, and nebulas, and other deep sky objects. I recommend joining the Royal Astronomical Society of Canada to participate in the telescope loan program if you're interested in buying a telescope. You'll have an opportunity to try out many different scopes and determine which one is best for you. And this brings us to step 4, connect to a community. You can find information about the Royal Astronomical Society of Canada Toronto Centre online at rascto.ca. And through RASC, you can learn about upcoming astronomy events, you can find more astronomy resources, and you can become a member of the club for additional benefits, like that telescope loan program I mentioned. I hope this guide has helped you to feel confident in getting started in astronomy. Enjoy those clear night skies.